Hello everyone, welcome to my channel. In this series, I would like to cover one of the most frequently asked questions in a lot of math exams. And in this very particular video, I would like to talk about binomial expansions, especially when the coefficients are not positive integers. So you might have known that with positive integers, we have a binomial theorem, which is you can expect things with n choose m, where sum of m is 0 and n, and in the form of, well, a plus a to the power of m and b to the power of m minus m equal to a plus b to the power of n, right? This result is very useful, but we really want something more generic, in a sense where the power n is not really a positive integer anymore. We have, in this case, we can have a fraction, or in some cases we can have a negative number. Okay, and then let's have a look at this question. Show that the first two terms of the binomial expansion of the square root of 4 minus 2x squared are 2 minus x squared over 2. Okay, so the general formula when n is not a positive integer is, well, we only deal with things in the form of 1 plus x to the power of n. Okay, so the first term is always 1, and the second term is n times the constant of k, nkx. And the second term is n minus 1, 2 to the factorial, kx squared. And it continues on with this fashion. So for part A, we can rewrite the thing as 4 minus 2x squared to the power of a half, right? Square root is a half. But we haven't put it into the form of 1 plus kx yet. So we might need to do is divide by 4, or take 4 out basically. So 4 to the power of a half times by 1 minus a half x squared, a half. Well, you can see that those two expressions are exactly the same, just apart from that I take 4 to the power of a half out, which is 2 basically, right? 1 minus a half x squared to the power of a half. And now we can use this formula now, so 2 times, well, 1 and then half times minus a half squared, so minus 1 over 4 x squared. And continues on with higher order terms, but we ignore here. So we might just expand the bracket. 2 times 1 is 2, and 2 times minus 1/4 is minus a half x squared with higher order terms. And you can see it's exactly in the form as they required. So you can show that, well, exactly as required. Now, part B. State the range of values of x in which the expansion found in part A is valid. Very, very important part, okay? So in generic case where it's 1 plus kx to the power of n, you must have that kx less than 1. Sorry, the absolute value of kx less than 1. And in this case, what we're really expanding here is 1 minus half x squared to the power of a half, right? So you can see that the kx here, or the thing x here, is basically minus a half x squared. So for part B, what we really need is minus a half x squared's absolute value is less than 1, or it's equivalent to x squared's absolute value is less than 2, which means x is between minus square root of 2 less than x less than square root of 2. So this is the range where expansion is valid. Notice you can't just say that minus 2x squared is less than 1 because you haven't taken out the factor of 4 here, right? You must wait until you have 1 plus something, okay? And the something must have absolute value less than 1. It's quite important that we'll talk about later. Now moving on to part C. Hence, find an approximation for the integral of square root of cos x between 0 and 0.4. Giving your answer to 5 decimal place, get your calculator ready, and fully justify your answer. So, what do we expect? 0, 0.4 square root of cos x dx. If you remember small angle approximations, cos x is roughly 1 minus half x squared. So you can rewritten it as square root of 1 minus half x squared dx. Roughly, okay, roughly equal to. And you can see 1 minus half x squared to the power of a half is roughly 1 minus 1/4 x squared plus some higher order terms, which we will just ignore. Okay. And this is relatively easy because now we can integrate this is a nice polynomial. This is equivalent to x minus 1 over 12 x cubed, right? Between 0.4 and 0. So you can write it as 0.4 minus 0.4 cubed over 12. 0.4 cubed, just type it out on calculator. To 5 decimal place, it is roughly 0.39467 to 3 decimal place. Okay. So you can see how many times we use approximation here? Twice. First time, approximate cos x as 1 minus half x squared, and approx square roots of 1 minus half x squared as 1 minus 1/4 x squared. Now, moving on to part D. A student decides to use this method to find an approximation for square roots of cos x between the range of 0 and 1.4. Explain why this may not be a suitable method. Any ideas? Well, you might just think we can just follow the same principle as part C. So basically, use approximation twice as approximate cos x first, and then using binomial theorems to approximate again. And we've integrated because we have nice polynomials and should have a nice, fairly easy result. But why do we think it not work? I think it links to part B, right? Because every time you're trying to use approximation, you really should be careful, like in what range of value of x you're approximating with. Your approximation of only works in a very, very fine region of x. And 1.4 compared to 0 is far, far off the approximation range. We do not talk about how precise is the approximation 1 minus half x squared to cos x here, but we do know that for approximating square root of 1 minus half x squared, you need to be between square root of 2, right? And we know that 1.4, well, even though 1.4 is slightly inside square root of 4, because square root of 2 is 1.414, we know that. But 1.4 is really close to square root of 2, right? Last part. We know that 1.4 is really close to square root of 2, which means the approximation might be far off here. Right, And think about it, if you compare it to something like half pi, 1.4 is quite close to half pi, but that's okay, that's okay. Yeah, we don't really need to worry about cosacs here. It's more about the binomial theorem that really we should worry about the convergence radius. First of all, it converge, okay. It will converge, okay. At this point, series expansion will converge. No problem with that one. But as we're approaching the boundaries, the approximation is not quite valid. It's not quite valid. And that's the reason you want to say, well, this approximation doesn't really work very well here. Okay, this action, it might look not that hard, but actually has some inspirations. So the first part, very standard, you just need to remember the formulas and do all the correct things where you must put in the form of 1 plus kx first. Well, x doesn't have to be x, it can be x squared, x cubed, it's okay with that one, but it must be in 1 plus something. And for the second part, it's basically assessing you the idea where it converges. So always remember 1 plus something, then the something must have modulus less than 1. Very straightforward. And for part C, well, it's quite important there for you to remember cos x is actually 1 minus half x squared. Other than that, you can see, just use approximation twice, not really too tricky, but you do need to justify. I'll probably just need to justify that, well, because it's 0.4 is quite close, I can actually use the approximation twice. They should not contribute to too much divergence here from the real solution. Okay, and for part D, it's exactly the opposite of what I just said, because 1.4 was way off 0, too far away from 0, and the approximation, even though it might converge, but it will be far off it. Okay. And think about another thing where you have convergence of a cos x, where cos x, if you want to say, well, it might just work in the convergence radius of 1, maybe? I don't know, you haven't proved it yet, but you can see 1.4 in any sense is just too far away from 0, and you just argue that because it's too far away, our expansion, our approximation is not valid anymore, so we cannot use this method to approximate the integral. Okay. So you might have think that you have wondered, what's the point of binomial expansion for those square root of 4 minus 2x squared? Because we want some nice analytic results from here. So for example, if you reach a point where 4 minus 2x squared is 0, namely x is square root of 2, you might be interested how far it approached 0. Is it approximating like x squared or x cubed or something? It's those properties that you cannot look at a function and say, okay, it's converged at this speed. It can't. But if you expand it in binomial form, locally, you will see that, wow, I have a very nice form because, in a sense, binomial expansion is basically infinite polynomials, and especially when you find in the case where it converges zeros, in those cases, it's only the first few terms that matters. It tells you about convergence rates, it tells you the shape of the graph, what it roughly looks like. It provides you loads of different views to analyze a particular function. Even if you can even use it to approximate other functions, right? For example, cos x, you can have a Taylor series expansion in this case for cos x, but we only need to look at the first few terms, make a binomial. First two terms actually. And that's why binomial expansion is extremely important. Later on, when you proceed in complex analysis in university level, you will find that, well, if you have a 0 at some point, if it's a po not too odd, if it's a 0 not too odd, then you will say it's approximate to the power of x minus 1 to the power of like any Probably some positive integer. Why is it important? Because the convergence speed tells a lot of things, and this course is a bit too far beyond this course, but I just genuinely want to show that how important it is to master binomial expansions. It'll be really helpful, because in real life, there aren't that many things we can just solve numerically. Sorry, there aren't many things we can just solve it. We have to approximate solutions in many cases, and binomial expansions provide you very powerful tools to help you solve it numerically. And I hope you find this video interesting. Bye bye and see you in next video.